Hello, today's topic is composite functions and invertible functions. So on the agenda, we're going to look through composite functions both through mapping as well as algebraic composition. And then we're going to take a look at inverse mapping and how you can determine whether or not a function is invertible through looking at its inverse output and input. And then we're also going to solve for inverse functions algebraically and what that means when you graph it. So a composite function is a way of embedding two iterations of inputs and outputs. So say that you have an input x, kind of like what we're used to, and then we put it through a function g. That means that our outputs here for the x are going to be g of x. And now say that we take this function once more, and then we put it through the function h. So in this case, we're taking the inputs of g of x and putting them into h of x. So we can embed them and call this h of g of x. So in a way, this notation with the circle h dot gx is a way of skipping over these two steps and going straight from the x into these double iterations of putting a function inside of another function. So we can do this algebraically if we take a look at something like this with g of x is 2x and h of x is x cubed. So say that we wanted to do h of g of x. Once again, let's remember that this means that you take the outputs of g of x and put them with x's in the h function. So that means that in the h of x function, we replace every x with 2x. So now let's write out our notation. So h of g of x. It can be a little confusing, so just remember that you still work left from right. So the dot represents that the g of x values are going to be the input, so they're going to retain their position to the right of the h. A lot of people get confused what function gets composited into which other function. So in this case now we go ahead and replace every value of x and h of x with 2x. So this is going to be equal to 2x cubed. And don't forget that with this coefficient, we still have to cube it as well. So our function is going to be 8x cubed is equal to h of g of x. So what this does is it helps us save time. Instead of finding the output values for g of x and then plugging them into h of x, now we just know that this composite function is like 8x cubed. So let's try another example here. So say that in this case, we want to find g of f of x. So in this case, that means that we replace all of the x values in g with f of x. So that's only going to be an x here, so we replace the x with 6x. So g of f of x is equal to 6x plus 2. And so this makes sense because if we kind of think about this function, what we're doing is we're taking the function 6x and we're replacing the x in it and then shifting it up 2. So it's basically the same function, just shifted vertically 2. So now we're going to talk about invertible functions and a process I like to call reverse mapping. So in this case, if we're used to our normal mapping, then we take our inputs, which are like our x values, and we draw the corresponding output values with arrows. So in this case, the 3 corresponds to the 6, the 4 corresponds to the 6 as well, and the 5 corresponds to the 8. So if you remember from what determines whether or not something is a function, it has to have a distinct input value. So the x's can't be repeated, but the y's can be repeated. I like to think about that with the y equals x squared function. For instance, for y equals 2, you get 4, and whenever the x is negative 2, you also get 4. But for something like the y equals x function, each value only has one moment where it replaces that value on the y's. So in this case, to determine whether or not this function is invertible, we need to reverse the arrows, hence the name reverse mapping. So in this case, the 6 would go to the 3, and the 6 would go to the 4, and the 8 would go to the 5. So this would not be an invertible function, because now if we're looking at it from right to left, the 6 is repeated twice as an x value, which means that it's not a function, because in order for something to be a function, it has to have a distinct input for every output. So now, to examine something that is a function that's invertible, it's usually called a one-to-one. So in this case, for our input, the 2 goes to the 6, the 7 goes to the 8, and the 8 goes to the 9. So whenever we reverse it and go from the 6 to the 2, it still retains that there's a unique x value, and it doesn't violate any rules of whether or not it's a function. So we can also find this algebraically. So let's kind of review. If we have a function like y equals x cubed, and we map it with the input values and the output values, negative 2 would correspond to the negative 8, 0 would correspond to the 0, and the 2 would correspond to the 8. So in any moment, whether we graph any x value, it's always going to have a distinct output value. So that means that we can find the inverse algebraically. So let's go ahead and practice doing that. All that means is that we take each x value and we replace it with the y value. So we have x equals y cubed. And so for this to be still a valid function, we need to make sure that the y is to the first power and without a coefficient. So the way we can change it back to that form is to take each side to the 1/3 power. So x to the 1/3 and y cubed to the 1/3. So now we get x to the 1/3 equals y. And this demonstrates the relationship from the output to the input, because the cubic root of negative 8 is negative 2, the cubic root of 0 is 0, and so on. By the way, please leave a comment with any questions or feedback you might have. It helps me make better videos, so all feedback is always appreciated. So now we can also visualize this through graphing. So say that we have our y and x axes, and we go ahead and graph our function y equals x cubed. It's going to look something like this. So there's two ways of thinking about this. You either find the inverse by switching the axes, so the y-axis becomes the x-axis. It's kind of like a reflection. I think the more straightforward version of imagining that is that we're reflecting through the line y equals x. And so now, to graph the cubic root of x cubed, it's like this function reflected on this line. So it looks something like this. So for a function to be invertible, it means that basically we're able to graph this reflection and it still passes through the vertical line test, which determines whether or not something is a function. So since on this function it's still continuous and there's no places that there's two y values from a distinct x value, it would still be an invertible function. So these concepts are very helpful for helping us picture how functions can be inversed, and I like both the algebraic and the graphing approach because I think they offer separate angles on approaching this topic. So please like the video and subscribe to our channel. We love the support and we'll continue to make instructional math videos. Thank you.